So we're going to wrap up this section by looking at hotspots and mantle plumes. So what we'll do in this video is explain how the Hawaiian Islands were formed, and we'll define this concept called the Darwin point, and explain how it relates to the lifespan of island chains. Lastly, we'll connect this idea of mantle plumes as a process that's forming island chains like Hawaii to other tectonic processes that we've considered so far. So looking back at this map of Earth, and especially the ocean floor, we now have tectonic ideas or processes to explain almost all the features we talked about before. We have mid-ocean ridges where new crust is being formed, trenches where subduction is occurring, island arcs where that material, the melting from the trenches, is coming back up to forming new sort of crust-like islands. We've got marginal seas that are enclosed by this process, and so on. But one thing we haven't really looked at so far is everything in between. Between the mid-ocean ridge and the subduction zone, it's not just abyssal plain. There's islands popping up, there's ocean plateaus, and that's really the goal of this topic here. And so people have been wondering about places like Hawaii for a very long time. If you look at Hawaii from space, it's obvious that the island chain is following a straight line from the site of current volcanism, Hawaii Island today, all the way down through Midway Atoll and on. So, and then, now that we can see underneath the surface of the Earth with ocean bathymetry, we can see that this continues on this bend up to the Detroit Seamount near the Kamchatka Peninsula. So what's unique about the Hawaii Emperor Seamount chain is that there's a progression of ages across Hawaii. So for instance, Hawaii is still being formed today through volcanic processes. The last major eruption was in 2018, so this is very recent and still continuous. Kauai, for instance, is the end of the last sort of major Hawaiian island, is around 5 million years old. Keep going back, Necker, 10 million years, Midway, 26 million years, and then these older seamounts here, these are even older. So there's a continuous age progression from currently forming islands to older islands. So after Midway and the neighboring atoll Kure, all of these islands, all these are not islands anymore, they're seamounts and guyo, so they're below the surface of the Earth. And then, this is around this point, this is where this prominent bend is happening, and the causes of this are still unknown, but we know this happened around 47 million years ago. Okay, so across this age gradient, it's not like these islands stay in one place. They're subject to huge amounts of changes. If you compare the elevation of the big island of Hawaii, 13,803 feet at the top of Mauna Kea, versus Kure Atoll, the last Hawaiian island above sea level, 25 feet tall. If you look at them from space, you can see there's a big difference. Kure is much smaller than the big island too, so these are totally out of scale. And obviously the surface of Hawaii is totally covered in recent lava flows that have cooled down, whereas these atolls are sort of circular, they're sandy, they're sort of quite different. So in thinking about what could be producing these island chains, there's a couple of things to realize here. The first is that Hawaii is not, even though it's really emblematic of this process, it's not the only island chain like this. You can see here there's a couple other island chains throughout the Pacific that have very similar trajectories. This is the Marshall Islands to Austral Seamount chain. You can see it has a very similar trajectory. There's also a bend here similar to Hawaii. And then there's a Tuamotu archipelago here, including places like Tahiti, and then up through the Line Islands up here today. There's a few other these really prominent seamount chains throughout the Pacific. And so when these were observed, this is confusing for a while, and then there was this idea that came around once plate tectonics became proposed. It made sense how these islands could be made in such a line. Instead of the source of volcanism popping up in different locations over time, you could have a fixed hotspot on Earth that, as the plate moves, could be feeding new islands over time. So the idea is that the Pacific plate is moving up here to the northwest, and then as it moves along, certain islands that are actively volcanic are being pushed back, and new ones are being formed. The old islands are cut off from this magma supply. So this was hypothesized. This hotspot hypothesis was proposed by Morgan in 1971. And the idea is that, yeah, they're relatively fixed in place on our surface, and it's the plates that are moving that creates these big island chains. So you can see that in more detail here. So here's a cross-section through Hawaii, and you can see there's this big hotspot here, this mantle magma coming up, burning its way through the Pacific lithosphere, and then forming in these more discrete channels different active volcanoes on Hawaii. So this one could be Kilauea, this one could be Mauna Loa, there could be an extinct part such as Mauna Kea, which isn't actively erupting anymore. There could be new islands forming such as Loihi off of the front end of the Hawaiian Islands. And then as the Pacific plate moves, eventually the big island of Hawaii will be moved further away and will be subject to erosion and won't be growing anymore through this volcanic source. And so it'll start to degrade. You can think of Maui as basically a partially, currently eroding part of the Hawaiian hotspot. Oahu, more eroded, Kauai, more eroded, and so on. So as islands are sort of separated from this active source of magma on the hotspot, they don't grow anymore. They start to be eroded by things like rain, like wind, and they also start to sink more in the lithosphere. So you can imagine that you're pushing all this new material onto the surface of the Pacific plate through these eruptions. It takes a while for the Pacific plate to sort of realize how much new mass is there and start to rebound through isostatic equilibrium. And so eventually, the islands, they cool, they become more dense, and they start to push further down on the lithosphere. And that's the process that begins their subsidence, that begins them to sink, as the Pacific plate ages and as they are moved away from the hotspot. So eventually this leads to the process of atoll formation. So this is basically a replacement of rocky islands with these rims of coral reef. So what happens here is that corals can only live in the photic zone of tropical island regions. They're basically constrained to around 100 meters below Earth's surface. So the island has to be, has to have area that is around that depth, or between 0 and 100 meters, for coral reefs to first start growing as a rim around the island. This is called a fringing reef. Eventually this will grow into a barrier reef, so the coral platform will expand outward, and then that'll create a barrier reef around a volcanic island. And as the volcanic island is subsiding, as it's sinking into the lithosphere, the coral reefs are actually able to continue their growth, and any sinking that might happen due to this isostatic equilibrium is compensated by more growth of the corals. The corals are producing calcium carbonate, and they're able to move upwards at a rate of around a centimeter a year. So the island is sinking, the coral reefs are rising, and overall things stay level. But you can see this transition that happens. This is Moorea in Tahiti. This is an island that's cut off from the hotspot. You can see it's eroded compared to where it started, and it's got this fringing reef. This is Bora Bora, and so you can see here that the fringing reef is much bigger. The sort of pinnacle of the island is all you can really see, and everything else is below sea level. And then eventually you have just sort of a round atoll here where you just have the coral reef. So one thing is you'll notice that these are sandy and not necessarily active corals. If during this process, at any point, if the sea level drops a little bit, what's going to happen is that winds, waves, all of their erosion forces are going to start pounding the part of that island that's above sea level, and so they'll start knocking it down, generating sand, and that's why a lot of these islands appear sandy at the surface. So here's a cartoon of this process. You start off with this active volcano. It's got a magma source coming up from the mantle, and then this fringing reef is built sort of around this island as it grows. And then the island moves along the plate. It's separated from this magma source. It starts to erode, but as it sinks down into the lithosphere, because it becomes more dense, the coral atoll, the coral reef keeps growing up, and that keeps pace with the sinking of the actual rocky island. And so you see this rim becoming more prominent. This is the barrier reef. And then eventually, the actual seamount, or the actual island, the basaltic part at least, will sink below the surface, and all you'll have left is this coral that's continuing to grow and keep pace with sinking. So this works for a while, but there's some limits to this. And this was proposed to be the Darwin point. This is after Darwin's observations as he was circling the globe when he was figuring out some things about evolution. So the idea is that there's a specific point where this process becomes unsustainable anymore, where basically temperatures become too cold for the corals to grow fast enough to keep pace with sinking. So that's the idea of the Darwin point. That's the point where you cross from an atoll that's able to be sustainable to be able to compensate for sinking by growing upwards with corals, to a process where the corals can't grow fast enough and everything sinks. So just to track the island journey over here, there's this first zone where you're building your barrier reef. Here the island is exposed above the surface. You can still see the remnants of the extinct volcano. And then there's a second zone where all the volcanic parts are submerged. You have this atoll that's starting to form, and all is good up until the Darwin point. And for the Hawaiian archipelago, this is around 29 degrees north. Above that, temperatures are too cold for the corals to really sustain growth, and then this atoll will begin to drown. And that's why we have a lot of guyot sort of in the further along Hawaiian Islands that have passed this 29 degrees north part where the water's too cold. Eventually, these keep subsiding into the Pacific plate until they reach the subduction zone where they're basically destroyed forever. So this is the sort of, this is the future of islands like Oahu. It'll take 50 million years for them to get here, but yeah, this is what's going to happen to all hotspot islands eventually, especially those that leave the tropics. If it stays within the tropics for a long time, there's no limit in theory to how long that these corals can be sustained, unless things like climate change affect this. So that's how these island chains end. How do they start? Well, so this mantle plume theory, it's been expanded to account for observations of what's called large igneous provinces or flood basalts. So the idea is that you have this superheated part of the deep mantle. It's right next to the core. It's receiving all of this heat. Once it has enough energy to liquefy and rise as this molten magma through the mantle, you're going to have this sort of plume head that's like doing most of the work in terms of carving out this path through the rest of the solid mantle. And then that reaches the surface and then erupts in these giant floods of volcanic eruptions, these flood basalts. So that's sort of the first step of an island chain like Hawaii being born. And then they're followed by this volcanic trail that moves away from this flood basalt. And this is sort of the state that we sort of know as generating something like the Hawaiian archipelago today. So one thing is that if you think about where the Hawaiian archipelago ends, it ends in a subduction zone. So it's very likely that the flood basalt that started off the Hawaiian island chain has been subducted and returned to the mantle. So there are other places on Earth where this has happened. One really great example that might be accessible to you is the Columbia River flood basalts in the Pacific Northwest. So this is a large igneous province that in the area of Oregon and Washington and parts of Idaho here. And this is now the hotspot that forms Yellowstone National Park. So Yellowstone is over here. You may have seen pictures like this, these like crazy hot springs where there's cyanobacteria growing. That's sort of accounting for the strange colors, that there's this weird life that lives here. There's all the geysers going in. So this is a hotspot plume in the mantle that's sort of melting part of the ocean crust. It's sort of making it's raising the temperature at places like Yellowstone. And it's sort of, unlocking all these sort of weird geochemical or geological processes there. But you can actually track the volcanic path back to the Columbia River flood basalts here. So this is Yellowstone today. And there's extinct volcanoes all along this track here to this large eruption. And here is the Columbia River basalts. This is what they look like. They look actually quite similar to Hawaii. They're just large stacks of black rock. So this is a map of the major large igneous provinces around the world. You can see that there's a large amount, and they've had various roles in Earth history, when they erupt. We'll talk later on about the Siberian traps, this large eruption in Siberia that is associated with one of the largest mass extinctions in Earth history. But there's also, they're located throughout the globe. So most of the time, you see these mantle plumes represented in these cartoons of this sort of ball of magma sort of working its way up through the mantle. We now have the technology to image what mantle plumes actually look like. It's the same kind of seismic-based imaging that we mentioned before. Essentially, you're looking at waves triggered by earthquakes and seeing how fast they pass through different sections of the Earth. And there's a lot of computing at the end of this, but you can basically tell if a certain part has been slowed down or sped up due to changes in density inside the mantle. So this is the Hawaiian Island plume here. This is with the big island of Hawaii right here. And there's this big area here of anomalously well, it's hard to tell exactly. It's probably warmer temperatures. It's probably in a more liquid state. This is the mantle plume rising up from the core boundary up to close to where we are today. You can see this is a much bigger map sort of throughout the entire North Pacific region. And you can see this is Hawaii here. You can see this is the mantle plume. It's started at the core where there's all this heat from the inner core, from the outer core going to the mantle, ends up in Hawaii. You can see a similar thing in Iceland. So Iceland has this double whammy where it's a hot spot and it's also on a mid-ocean ridge. And you can see there's this plume coming up from the core boundary up through Iceland. Interestingly too, you can see there's a much larger plume underneath East Africa. So we'll come back to this in a second. So one of the things I think is just really cool about this is that, for a while people thought that hotspots were just isolated around the globe. They were just happening, where conditions were right, and there was no sort of further story to this. But more recently, due to this kind of imaging of the mantle, we can now see there's really two major places of hotspot generation. These are called, these are mantle provinces at the bottom of the mantle at the core boundary. But there's one really big one sort of surrounding Africa right here, and it's feeding all these different hotspots, especially the Tristan da Cunha and the Reunion Island hotspot in the Indian Ocean. And then there's another big one of these provinces that are feeding most of the major hotspot island chains in the Pacific. Hawaii, the Louisville chain, which sort of forms a really nice line all the way over here, Easter Island, Galapagos, all of these guys seem to be fed from the same source at the bottom of the mantle. So here's just a quick summary for how this probably works. You have these regions of superheated, basically super plumes forming at the core mantle boundary. These are leading to hotspots on the plates. But one cool thing is that this is not an isolated feature. They're connected to plate tectonic processes at the surface of the Earth through subduction zones. So for instance, here you can see this is the Pacific plate, this is the Nazca plate being destroyed as it subducts underneath South America. And the densest part of this are sinking down towards the core boundary and becoming part of these superheated provinces that are going to come back up to Earth's surface as hotspots. You can see the same thing here with subduction zones. This is the Marianas Arc. This is the Indonesian subduction zone near Sumatra. And yeah, so this is another cartoon of this, but you can basically see subduction of some type of plates coming down all the way to the core boundary, heating up as they're in contact with this heat source, and then liquefying and returning back up to the ocean to the surface of the Earth as a large igneous province or as a hotspot. It's unclear why some plates reach the deep mantle and the core boundary, and some, like the Japanese, the Pacific plate that's subducting under Japan, seems to level out at some regions. Maybe it's related to plate temperature. The truth is we don't really know. But to summarize what I've just been mentioning, mantle plumes and hotspot volcanoes seem to originate from two deep mantle provinces. One is below the Pacific and one is below Africa. So some of the subducted crust in subduction zones is cold and dense enough to reach the bottom of the mantle. This then heats up, feeds back into the hotspot, and then is actually part of what's forming Hawaii. In addition, these large mantle plumes can collect underneath continents. This is what's happening underneath Africa today. And this helps provide the extra heat needed to trigger this continent-continent divergence we talked about before. This is happening underneath East Africa right now. That's this mantle plume that we showed before. That's what's coming up, melting some of the crust, allowing, pushing some of the plates apart and creating this divergence. So this may also happen to some extent in mid-ocean ridges too. So just in closing, I wanted to revisit this animation of the history of the breakup of Pangaea over the last 180 million years or so. You can see there's large igneous provinces here marked in black. This is the one in Siberia that we'll talk about later on. During this process, right, we're seeing the formation of this mid-Atlantic ridge. This early Atlantic is opening. We're going to see the seafloor striping start to come up as new crust is made in the center of the mid-Atlantic ridge and pushed to the side. So this is what's pushing the continents apart. You can also see in some areas, this Gondwana land is starting to break apart, and you're starting to see these large igneous provinces popping out right when the spreading starts to happen, which I think is really neat. Right here you can see there's, what is this? This is Antarctica, and a bit of and Africa here are coming apart, and there's this large igneous provinces that may be pushing them apart. Same thing here, South America, Africa. There's large igneous provinces that are sort of coincident with the starting of spreading. Now the other thing you'll see, here's another one coming up, it's going to be pushing India towards Asia. And you'll also see, if you look on the other side of this, all these exotic terrains and island arcs accumulating around Alaska here. This is going to be forming, this sort of series of island chains are going to be forming what we know as Alaska today. The Farallon Plate over here is being subducted underneath the coast of California. It's generating the Sierra Nevada, generating all the California volcanoes that are now extinct. And things keep going. Look at India taking off. It's ramping up for this collision with Asia here. You can see it may be powered by a large igneous province that's erupting right at the spreading center. That's still a bit controversial. And as this is happening, the Pacific Plate is sort of shifting a little bit too. And one of the ideas for why the Pacific Plate shifted is because of this collision with India that sort of forced this global realignment. Again, not everyone subscribes to that. It's an idea. It's not fact. And then you can see things like Iceland pop up too. This is helping just to push apart Greenland and northern Europe here and sort of create the northern part of the mid-Atlantic ridge. And that's the continents that we have today. So this is sort of, hopefully now you have the tools to interpret things like this over Earth's history, to appreciate some of these changes and how surprising they are. So in this video, we've explained how the Hawaiian Islands were formed. You can imagine the plates moving over a fixed hotspot in place, and then new islands are formed when they're underneath the hotspot, and then they move along, and then they're cut off from the hotspot. They start to subside and sink back into the mantle because they become more dense, and because isostatic equilibrium will push them down deeper into the mantle, away from the surface of the ocean. And at some point, the corals that are compensating for the subsidence can't grow if the waters become too cold. That's the Darwin point. So that's what causes islands to drown. That's why the northwestern Hawaiian Islands are atolls, and then once you reach 29 degrees north, everything else is a seamont or guyot. And then lastly, we've looked at mantle plumes in forming things like the Hawaiian Islands, but also in triggering some other big tectonic processes, such as the current breakup of Africa and also the past breakup of Pangaea.